I'm Roger Rohrbacher. That's Rohrbacher.
And how did you happen to come to Hanford?
In 1942 and 43, I was working for DuPont in an acid plant in Illinois. And my buddies were disappearing. And they ended up in Richland. So I got the map out, and Richland, Pasco, Kennewick weren't even on the map. So I contacted them. I said, "What are you guys doing?" They said, "We don't know." And then another guy interrupted, having only one phone. He said, "It's sure desolate out here." So a couple of weeks later, my boss said, "There's a guy wants to talk to you about a new job." You know, young and single. I said, "I'll take it," assuming I'd end up here in Richland, whatever that was. And he says, "Report to Dr. So-and-so, University of Chicago, 40 miles away." And here I thought I'd see the Great West. And this was part of the Manhattan Project, and I was assigned to an engineering development group, and we were dipping samples of aluminum in water, checking for corrosion and film buildup. And it wasn't until years later I found out that somebody had shipped 5,000 gallons of Columbia River water to the University of Chicago, and this is what we were doing. These were the process tube and the jacket material for the fuel. Okay, I came out here and ended up in Pasco at 4 a.m. or something like that. My buddy was supposed to meet me. He didn't show up. Well, it turned out that another fellow from DuPont said, "Oh, we'll give you a ride in." They did. Then I made the mental note, this guy better have a good excuse. Well, it turned out he was in the hospital. He had an appendicitis attack, and they were on surgery that morning, so we let him go. I ended up in the transient quarters, which was a Corps of Engineers building, for a couple of days, and then moved into a dormitory. And I presumed I'd be doing some chemical work and so forth. But during the interview, this fellow said, "We'd like to have you in the instrument department." And I always said, "Hey, I play a trumpet, boy, I'll fit right in." And he says, "What do you know about instruments?" And I said, "Nothing." He says, "Do you know what an ammeter is?" And I said, "Yes." "Okay," he said, "we're going to give you class training, and we're going to give you hands-on training and so forth. In about a year, you'll know everything you need to know." Well, that's not quite true. I ended up mostly in BD&F. I came out here in April '44. I worked on instrumentation, mostly flow and temperature and pressure, and then later on radiation monitoring. Matter of fact, that was one of the clues what was going on. None of us really knew, except maybe a dozen or so of the scientists. Something came up, maybe 8 months after startup. They had some problems with the chambers monitoring neutrons. And the foreman said, "Move this neutron chamber, a couple inches one way." I said, "Well, I had a whole year of physics. This ain't no chemical plant," because that was the story. Big chemical plant. What else does DuPont do? So I was in training for a while and worked at her, mostly in the reactor building, concerned with the equipment to measure the neutrons and the pressure and so forth. Each process tube had a flow monitoring device, and the exit of each process tube had a thermocouple to measure temperature. This is part of DuPont's program, I might say. It's diversity. One of the main concerns in the reactor is that you had good cooling at all the time. And by monitoring the flow, that gave you a good clue. And if that did not respond properly, you had a temperature measurement on the outside. If it got too hot, you knew you were in trouble. That was one of the problems. Everything was, what you might say, fail-safe, like what they call the Panot gauges to measure the flow. They were all in series, 2004 in series, something like a Christmas tree string. One bulb goes, they all go, and shut down the reactor. And they call this a scram. This had to do with Enrico Fermi's first pile in Chicago. Their safety equipment was a rope on a safety rod leading down to a post. And there was a man standing there with an axe. And if any trouble came up, he was supposed to chop the rope with an axe. They call it safety control rod axe man. Whether it was ever used or not, I don't know. And here that term came to use for any unexpected scram. And of course, there were a lot of reasons for doing that. one of the things that they came up with was how do you measure a small amount of current? And this was used a galvanometer, and it was a mirror suspended on a very fine thread. It had little magnets on the side and the coils, and the small electric current from the chambers moved this mirror. And we're talking about small, a millionth of an ampere. And these, this equipment was, pre-World War II stuff. Vacuum tubes, a cubic foot of vacuum tubes, maybe 15 vacuum tubes inside. And that detected a small amount of current. Anyway, there are a lot of other features in the reactor to monitor for what was going on. And if anything failed, they'd automatically scram the reactor. The reactor had 9 control rods, which were horizontally controlled. And these were electrically driven, at least initially. And later there was another system that provided hydraulic force. And the operator would slowly pull out these rods to start the reactor, and then monitor the rate at which the reactor was increasing in power level. The power level is generally measured in half-life, or how fast it takes to get from one particular power level to another. And the operator was careful during startup, but during operating, when everything was normal, it was quite simple, relatively speaking. It's like the car in cruise control. If you have no traffic in front of you, you don't need to stop, you just sit there. And the operator sat for 2 hours at a time in the control room, and there's generally one other operator reading other gauges and so forth. And there's also a panel that caused an alarm. A red light flashed and the bell rang if something unusual occurred. And then, if minor adjustments had to be made, he would move one control rod maybe a half inch at a time. And of course, when there was a trouble, the reactor scrammed, these 9 horizontal control rods would go in the reactor, and 29 horizontal or vertical safety rods would drop in the reactor, and that was automatic. A little story on the side about these rods. Enrico Fermi came out here at one time when they were testing these rods, and he was concerned that they were testing them so much that they'd knock the bottom out of the tube in which they were contained, called thimbles. He said, you ought to put a spring at the bottom to stop the jolt or somehow reduce it. And that information has now been declassified, and his code name at Hanford was Eugene Farmer. And the letter says, Eugene Farmer came out here and so, and he was reasonably happy what was going on, but didn't like our testing program. I thought that was kind of interesting. Well, one other problem with the early days before computers, the Panlet gauges were 2004, and all the readings had to be taken once a shift. And then in a similar matter, all the thermocouples that monitored the temperature had to be recorded twice a shift. So a tremendous amount of work. Some of the instrument people came up with a deal to avoid this called a flexowriter. They went to a couple of typewriter people, and the typewriter people said, it's impossible what you want to do. They said, well, send us a typewriter anyway. And 2 typewriters came out, and their names were removed, the little name tag. So they said they didn't want to have any part in a failed operation. It turned out it worked. And this flexowriter could automatically monitor all the process tubes and record their temperatures on a sheet of paper. And that was a real improvement along the way. Well, we had some problems with the reactor along the way. One was graphite expansion. Because of the radiation, the graphite expanded to the point where the fuel elements couldn't pass through the process tube. It was bowed out like a hump in the middle. The first solution was to make 4-inch fuel elements instead of 8 inches so they go through easier. Then they're looking for a permanent solution. They decided that maybe if they could get the graphite hotter, it would reduce this growth. They call this annealing. So they mixed the gas. The original gas in the reactor was helium, was used just to keep the air out of the reactor. They mixed that half and half with carbon dioxide, and that caused the reactor graphite to heat up. And that heating apparently stopped the growth and maybe even reduced it a little bit. So that was an interesting facet. Another problem was fuel ruptures. If there's not good bonding between the uranium, the metallic uranium of the fuel element, and its jacket, you'd get a little water inside, and the reaction between the water and the uranium would bulge out the fuel element, and it would stick. And if it got bad enough, you couldn't even get it out by pushing on it. Sometimes the whole process tube had to be removed. So that was an interesting experience. But the rest of the operation went pretty well. One of the problems and concern was, do you have a problem that needs to be shut down or do we not? And generally they tended to wait until they knew they had a problem because of the need for production.
How many times was it scrammed?
Pardon?
You can recall, how many times did they have to scram the reactor?
Oh, in the early days, sometimes a couple times a week. Matter of fact, it got so bad in the early days that...
Start that again, because she was talking at the same time.
Oh, okay.
Start again within the early days. That happened a couple times a week, the scram.
In the early days, the reactor scrammed quite often, sometimes a couple times a week. And most of the time it was due to the panel gauges would just get a little bit off scale, and when one of those things happened, it would scram the reactor. There even was a feeling that we can just do away with these panel gauges and take them out of circuit. And they tried that for a few months. And then they said, gee, this is not too bright a thing to do. So they put it back in. And they got a deal to rearrange the system so that it operated better. And one of the problems, of course, more water flowed through the center of the reactor than the outside. There's actually 3 or 4 zones. And each panel gauge in each zone had to be almost individually set. In the early days, all this setting had to be done behind the panel, and after a couple of years they decided to move the adjustment knob to the front. So that helped a lot in that regard.
What was, you worked for DuPont before you came to Hanford. What made DuPont a good choice for this project? Well,
DuPont was known for construction of plants and for chemical plants and so forth. And they were noted for a couple of things. One was their safety aspects, and the other thing they called contingency. I never heard of that term used in a plant till I got in this acid plant in Illinois. And our group wanted a storage tank for what they call a sales acid. If it was below 68%, they generally sold it. And the designer said, well, what size tank do you want? I said, well, about 4,000 gallons ought to do it. He says, what's your contingency? I don't have any, that's what we need. He says, okay, we'll put in a 4,500 gallon tank. And I came out here, and this was a story with General Groves and Crawford Greenewald. The story was that Enrico Fermi said 1,500 tubes was sufficient for the reactor. And Crawford Greenewald went to General Groves and says, what's your contingency? He says, Fermi says 1,500, it'd be 1,500. And Greenewald said, if something went wrong with this plant, who do you think would get the blame? And, the old general was a pretty sharp guy. He says, how many more tubes do you want? He says, 500. So they put in 500 tubes. And without that, the reactor probably wouldn't even operate. So it was a fantastic thing. Matter of fact, in the early days, all the reactors were given only a 50-60% chance of operating. Which brings up another question I'm surprised you didn't ask. How come there's no A reactor? In the early days in Chicago, the plan was to build 8 gas-cooled reactors. And then they had some concern, how do you contain helium and how do you do this and that and so forth? So they changed their view and they said, well, we'll build 3 water-cooled reactors, and that would be the same process. And this is another little sidelight. This is a story I heard that Fermi was always considered exacting and knew everything, so forth. If he had any question, he'd whip out a slide rule and come up with the answer. So they said, well, if we're only going to build 3, and now they have 8 sites lined up, A through H, how far apart should these reactors be for safety? And he says, 5 to 10 miles apart. We're expecting something to the nearest foot, and he ended up with a 5-mile variation.
What about, getting back to the xenon problem, which was what necessitated the use of the rods that were designed in as an afterthought. Could you explain what that problem was and why the extra rods, the extra capacity solved that problem?
Okay. Because this whole project, Manhattan Project, was going full speed, and all the answers were not known. And when the B reactor was first started up, things went quite smoothly. They started pulling out the control rods, and the power level went up, 50, 100 megawatts and so forth. And not all of a sudden, but over a period of time, as they pulled the rods out, the reactor power level kept going down and down. They had all the rods pulled out, and the reactor was still non-functioning. It was zero power level. At this time, they were concerned with what's going on, and I'll have to tell you a little bit about security. This area here was top secret. Most of us had, or secret rather, and the big boys and the superintendents had top secret clearance. And a room right next to this was a top secret room, and Enrico Fermi and Crawford Greenwald, John Wheeler were there, and they were talking away, and Fermi was waving his hands around and so forth. And Bill McHugh was there at the time, and he talked to his boss. He said, "Go by the door and see what those guys are doing." And the superintendent comes back with all smiles. He said, "You wouldn't believe it. They're setting up a pool to guess when the reactor would start on its own, and the winner will get a bottle of wine." Here was an earth-shaking event, where the reactor worked or not. And then they finally decided that during the reaction, one of the fission products was iodine, and it's decayed to xenon. And the xenon was a strong neutron absorber. And when the process went on to where xenon was generated, it absorbed all the neutrons and had to shut down. And one of the ways that made it work is the additional 500 tubes provided more neutrons so that you could start up again. But you could not necessarily start up right away. Normally you have to wait for the xenon to decay, and that was a fairly short half-life, maybe, 20, 30 hours. They usually wait a day and then start up. Or what they had, if they knew right away when the scram occurred what the problem was, they had a quickie startup. If they could start up within 20 minutes, they could go ahead and do that. Put the rods in where they were and hope everything's okay. And then, of course, later on, I would guess early 50s, enriched fuel was used, which had more uranium-235 and more neutrons were available. So that halfway got rid of the problem along the way.
So let me see if I can get this right. Then even though you had more neutrons for the startup, but you still had the xenon. So the extra neutrons would overpower the xenon until it decayed sufficiently. Is that how it worked?
Well, I mean, to start up?
Yeah.
Yes. Yeah, when you first started, there was no xenon there. And as the reactor started to operate, xenon was built up. And as you built up the xenon absorbed neutrons. So the neutrons were not hitting more uranium and generating more neutrons and so forth. So by providing additional fuel elements, more uranium, they overcame that. And there were still restrictions, but that was generally the problem. And then, of course, it was pretty well solved with enriched fuel that had more uranium-235, where the neutrons came from.
You'd be great at this, I got a feeling. But, at some point, this film will not go for it's not for engineers, obviously. Could you give a good lay description of what this reactor is to a lay person who doesn't know what this reactor really did? Just a simple lay description of what it does.
Well, the core of the reactor is a big cube of graphite. Graphite is like charcoal, carbon, and it's about a 35-foot cube. And this graphite reduces the energy of the neutrons. The neutrons come from the uranium. Uranium dug out of the ground is naturally radioactive, and it has two parts. Uranium-235, which generates neutrons and is radioactive, and the other uranium, uranium-238, which is not radioactive. And in the reactor, the neutrons from the uranium-235 are reduced in energy and hit uranium-238. And that process is we call transmute uranium into plutonium. And in this process, this fission process, a lot of other products are also formed. I'd say maybe 12, 15 other products, isotopes of cobalt, strontium, cesium, and so forth. But the only one of great concern was plutonium. And another concern with the reactor, after you made plutonium, it took about maybe 2.5 days for the process from uranium-238 to plutonium-239. However, the reaction does not stop then, and the uranium-239, which is the weapons-grade material, converts to plutonium-240, which is not weapons-grade. Well, you could probably use it, but why not use diesel fuel and fertilizer? It's not that great. So during the operation, the reactor was shut down every month, and the central process tubes were discharged to get the maximum 239. Then the intermediate tubes were probably discharged 5 or 6 months, and the peripheral tubes maybe once a year. So that way they got the maximum plutonium-239, what they want. Matter of fact, that was about the time computers were coming into being. And one of the manual jobs was how do you decide which tube to discharge or how many discharge at what period of time based on the neutron flux. How active were the reactor and so forth. And that was monitored by the temperature rise and the flow. And this was a top secret thing. And a special man did this every day, and he kept it in the bottom drawer of the safe, top secret, stuff. And that was used to determine the maximum plutonium-239 coming out. And that was another interesting process, discharging the fuel. The reactor had to be shut down, but you had to keep a small amount of water flowing. You took the caps off the front and the back of the process tubes and pushed out the charge of metallic uranium that had been irradiated. And that dropped into a pool of water. It dropped through the air for about 20, 30 feet, and then got into a pool of about 20 feet of water. And to stop the blow, they put in what they call a mattress pad, which was rubber or plastic or something like that. And the fuel elements, they were 8 inches long, about 1.5 inches in diameter, and they didn't want them to drop on the concrete and break, so this mattress pad stopped it. Except the radiation was so terrific that the mattress pad got brittle, and the fuel elements would fall through. And then there had to be strict accounting for all of these, and they're searching all over the basin to find them. And the ones behind or underneath the mattress pad, they couldn't really get to. So they turned off all the lights, and the Cherenkov glow from the irradiated fuel elements showed through so they could get a tong and pick them up and put them in there. And this was another great concern. Where's the security man? He's still there.
He hasn't said anything yet.
The buckets were loaded. The bottom layer was laid in all horizontal, and then the second layer was laid in at right angles, and I think there were 64 fuel elements in a bucket. And then just to confirm that all that the count was right, they weighed the bucket before they put it in the storage area. One great concern by the Atomic Energy Commission those days is to account for every fuel element. And that was tough to do, thousands of these things. Well, 64,000 fuel elements in the reactor, and they discharge a third, that's quite a bit. And each shift had to check to make sure everything is right. However, quite often, they would be short or long fuel elements. So they had a separate hiding place where they kept it. And one of the operators said, one time we were so short we had to steal from another guy's secret supply to match him on the way. But what can you do with fuel element? You pick up a fuel element, you get a lethal dose in 15, 20 seconds. And matter of fact, even after the reactor was deactivated, I think they found a few along the way.
Where were they stored?
Pardon?
Where did they store these?
Oh, hidden in away some corner someplace, or maybe a bucket that said, "Do not use, B shift only," or something like that. And of course, another particular problem was occasionally there would be a mistake, if you might say that. And to discharge a process tube, you had to take off the cap front and back, and then push the fuel out by putting in new fuel. Well, they somehow got the cap off the front of one tube and the cap off the back of the adjacent tube. And the guys were pushing and pushing. They said, "What's going on here?" And they pushed so hard that part of the thing next to the nozzle in the reactor is called a gun barrel. It's a steel thing about 7-8 feet long. It started to come out of the reactor. So they said, "That's enough. We got a problem here." And other problems, the fuel elements would somehow get stuck on the elevator. And this was another interesting thing. The operators got a fair amount of radiation, so they always picked the supervisor or an engineer to take care of the problem things. And one of the supervisors, Bill McHugh, tells the story that they told him he got an element stuck on the elevator, and they gave him an 8-foot pole, and they said, "You run out there and try to dislodge the fuel, and only try twice. Whether you get it or not, get out of there." So he got in the first time, and he was running backwards so fast he ran over the radiation monitor that was monitoring his radiation along the way. So that's pretty good.
Let's see.
You were telling just some stories about what people had said about what was going on out here.
Oh, yes. A lot of rumors. Everything was coming in, nothing was going out. And some people said, "Oh, that's a sandpaper factory." They hold up a glued sheet of paper and the dust coats it. And another one was FDR's winter palace. He's going to convert one of the reactor buildings into a thing. Of course, they didn't know it was a reactor building at that time. And another one, the show and tell at school, the kid says, "I know what they're making. They're making toilet paper." And my dad brings home 2 rolls in his lunch bucket every day. Incidentally, one of the persons left the plant with a bunch of copper wire wrapped around his waist, and the patrolman gave him a pat search and said, "Step over here, please," and the rest of us went on. We never saw the guy again. And another story was that they were making horses' front ends. And the question is, what are you going to do with those? Send them to Washington, D.C. and connect them up. Anyway,
I'm losing control here. I'm trying to remember what else we need because this has been so great.
You have really hit lots of buttons.
pardon?
You have given us a lot of material that is going to be perfect.
Tell us about the people here, though. I mean, was there pride in the work? Were they, what were the people like? Because, like at EBR1 when we did that piece, these guys were pioneers and they knew it. And they really had a sense of it. Did people have a sense of what they were doing and how important it was here?
Yeah. I think that's true. The people were dedicated, and of course, most of them in the early days came from other DuPont plants. And then, even though they didn't know what they're doing, they did what they're supposed to. And I think there's a pretty little kind of a comradeship feeling that we're doing this and so forth. And the thing that surprised me, of course, after a few security lectures, you never talked about it. You go to a movie, and here'd be big letters about it, 1.5 feet high. Silence means security. As a matter of fact, there's another story about security meetings. They're supposed to be a half hour long. They tended to be longer and longer. So we convinced the security people to have the meetings at 11:30. So and these were the days when there's no cafeterias or anything out there. 12 o'clock, plus or minus a few seconds, we'd all rattle our tin lunch buckets, and the security guy got the message. But we didn't know. And matter of fact, the FBI checked us all over ahead of time. I remember my mother called me up and said, this is back in St. Paul, Minnesota, said, "Roger, what are you doing? They're asking all about you." So I came out here, and then, of course, we did get a bunch of security lectures, and we did really get told what we're doing, although we got the impression. One thing that Bill McHugh told a pretty good story. He said one of his operators was hefting one of these fuel elements. And he says, "You know, Bill, I used to work in a uranium mine in British Columbia, and this feels just as heavy as uranium." And Bill says, "Oh, that's interesting," and he walked away and didn't want to spill the beans. But nothing really was said. We had, well, what are you doing here? You end up with a few pounds of stuff, and we got an inkling, but not until the old village newspaper came out and said, "It's the bomb," that we knew what was going on. But I think, matter of fact, a reporter from the TV station in Seattle came here and interviewed a bunch of us, and we told about security, and she said, "Well, that wouldn't be the same today," which I think there was a little different attitude. Yeah, we had bridge clubs and meetings and so forth, the volleyball and so forth, and we never talked about it. And of course, volleyball, it dehydrates a guy. You have to go to the Gaslight Tavern and drink water, of course, to get your liquids back. But nobody ever said a word that I know. Just a good secret.
That's what they maybe didn't even know it was uranium that was coming out of these reactors.
Yes, that's true.
A lot of surprise.
Prior to the announcement, most of the people did not know. There was probably a dozen in the early days during startup, and maybe 3 or 4 dozen later on. You can't very well operate the reactor without having a little clue what's going on. So I would say that's probably true. And even like myself that had pretty good suspicions, we didn't really know for sure that this was going to end up in an atom bomb. We knew physics was involved and we knew uranium was involved, but that was about it. We just kind of got the stuff by osmosis. Nobody ever said.
Yeah, some of the guys who were at the Manhattan Project in Los Alamos said that they were only told certain things, compartmentalized things. But
Through, like you say, osmosis, a lot of people figured it out. Was it easy to figure out here? Was it still pretty difficult? Was security pretty tough?
I don't think any of my acquaintances figured it out. Of course, this was another of these.
I'm sorry, do me a favor, because you won't hear my question. When you say figured it out, instead of using it, say figured out that we were working on material for a bomb. So go ahead.
I was under the impression that most people did not realize that what they're doing would end up in the atomic bomb. I think they were just kind of guessing and stuff along the way. They got the impression it was something other than a chemical plant and other than anything else, and they considered something to do with physics. And the operators themselves, of course, they were operating the plant based on the neutron production, so they must have had some clue. But people who worked in the 100 areas could not go into other areas like the separations area where they separated plutonium from the other stuff, nor could they go in the laboratory closer to town or where the fuel production was made. Only with a good excuse to find out some particular problem related to the reactor. In my case, for example, if there's some instrumentation I wanted to know something about, I could go some other place. But nobody ever talked about what they're doing. It's quite interesting.
Roger, whatever you're doing with your hands, rubbing them down there, I'm hearing it. It's making a squeak or something.
Pardon?
You're rubbing your hands on the inside of the bottom of the chair?
Oh, you can hear that?
You bet I can.
It's pretty sensitive microphone.
Okay.
Anybody else? Do you have anything?
I was just going to ask you, when you found out it was the bomb, what was your reaction personally?
Well, when the official news came out that it's the bomb, as the local paper said, it's kind of a surprise and relief, and halfway said, "Oh, I suspected something like that," but I think most of us really didn't, and it was the most surprising. And then, of course, we got all the little stories about how this came on. Didn't you know what they were doing? Yeah, they're sticking stuff in the reactor. Of course, called piles in, but I don't think maybe 95% really knew that it would end up as an atom bomb out of Los Alamos.
How did the attitudes change the next day you came back on shift, after you knew what had happened here at the Hanford site?
Well, I don't remember any particular change in the people after they knew it was an atom bomb and they were making plutonium for that particular reason. Matter of fact, that's come to think of it, there was some information out prior to the announcement that talked about how much product was being made, and all these 10 tons of uranium, and they're coming out with pounds of this stuff. What's going on? But I think the answer is it probably didn't change their attitude much. They're still, well, the war was still going on. The Cold War, getting hotter, and they built more reactors. C reactor was kind of partly built as an experimental reactor with a slightly different design, and also as a replacement for B. B was shut down for about 6 months because of the graphite expansion problem. And then there was a replacement for D reactor called DR. Well, that's pretty good. D replacement sounds pretty good. And then they built a replacement for F reactor called H. And then, of course, later on, the K reactors, K East and K West, were built, extremely large, maybe twice the size as the original reactors, about 4,000 megawatt thermal power generation. And then, of course, later was the N reactor, which is a dual-purpose reactor, made steam for electric generation and plutonium at the same time. That's where I ended up in working on N reactor design, and then in the instrument group concerned with safety aspects. It was a reliability analysis group, and we were to determine what might fail, how often, and what to be done about it. Some interesting results came up. One is there's nothing wrong with a simple system. We put in all these complications. What if this valve doesn't open? We'll put on a second valve operator. What if the second valve operator doesn't get air to operate? We'll put on a liquid nitrogen or a nitrogen tank to provide that in case there. It got so bad, the best, most reliable thing was have a simple system with a manual override. So if a guy really wanted to open the valve, he could push a button and the valve would open. So that was kind of interesting. And we went through this. Matter of fact, this is the days when the computers were just getting into being. We had this big thing called a fault tree. Everything that could cause damage to the reactor was put on. We had something like 32,000 inputs which would cause the reactor problems. And the computer at that time, this was a Boeing computer in Seattle, was so skinny compared to today, they had to divide the program into 2 parts. And of course, this is also the days of Fortran, where we had these cards, punch cards, big boxes of cards, shipped them to Seattle, and 2 days later they'd ship the stuff back with the answer. That's another place we had a lot of women. We call them girls, even though one was about 65. And they knew as much about the programs we did, and we'd ask her to do something. In one particular thing, like in the water treatment plant, we said, make up a bunch of cards that have the top part relating to the water treatment plant. And the answer would be, oh, we knew you'd need those. We did those already, which I thought was pretty good. That was a nice time.